Okay, section 5.3, part 2, picking up from where we left off the last time. So this should be the next sheet in your booklet, and we're going to look at where f prime and f double prime, so first derivative and second derivative, are positive, negative, or zero. So we've got two copies of the same graph, so we're going to do all of the f primes here and all of the f double primes on the second column. So we are going to look at, okay, what do we know about where the first derivative of this function is going to be equal to zeros, positives, or negatives? We know that if we have a max or a min, those max or min points, we're going to have a zero, right? F prime at these 2 points is going to be equal to 0, right? In between those 2 points, we have all of that slope in between here and here. Each and every single tangent that we could draw there has a negative slope. So this whole section is negative. Every single tangent that we drew here is a positive slope. Every single tangent that we could draw here is a positive slope. So we go from a positive first derivative to a negative first derivative to a positive first derivative, right? And if we were to figure out a function that looked like this, actually do the derivative, graph it, that's what it would look like, right? So we'd have it above the x-axis, below the x-axis, above the x-axis, and equaling 0 at these 2 points. It looks like 0 and 2. Okay. The second derivative, remember that that's looking at concavity. So I'm going to call this point here, where it's going from, okay, concave down, right? So see how this whole thing is like kind of a sad face, and then here's my happy face, right? Or a soup ladle, right? Here we've got from this point to the right, everything's concave up, so positive. From this point here to the left, everything's concave down, so negative. Okay, so same deal for these next two graphs. We've got f prime at x and f double prime at x. So f prime, we know that any max or min is going to be equal to 0. And then between those points, we're going to have positive or negative. So here we've got positive, a negative slope, a positive slope, and a negative slope. For our f double prime, we're looking for where it changes concavity. And this one's a little bit more guesswork, there-ish, and there-ish. So see how happy face, sad face, and it's not super exact, kind of anywhere in that ballpark I would accept, but definitely like not up here. That's not a good spot to put your concavity change. So kind of in the middle generally is where it should fall. But those are our 2 spots of 0. Here we know that because we've got kind of a smile, we could put soup in there. This is all positive. We've got negative, and we've got negative. This one, we've got, this is so crooked. This one we've got, again, we'll do f prime at x here and f double prime at x there. So we've got here is a local, it's not the absolute max, but it's definitely a local max. It's going to be 0 right there, right? And kind of to the left of that, we can see we have positive slopes. To the right of it, we see we have negative slopes. So I mean our first derivative is positive, first derivative is negative. Here, if we were to draw tangents anywhere there, we would see negative slopes over there as well. If we were to draw tangents anywhere over here, we would see positive slopes. Okay, so we've got positive, positive, and then negative, negative. Over here, we've got concave up and concave downness. You guys can see that all of this is like one big sad face. So this whole middle section is all negative. All of this is concave up, right? It just never actually like turns into a ladle, but it's definitely pointing up, right? That curve is pointing up. So these guys are both positive. So it's a type of question that you could see on a quiz or like an assignment, those sorts of things. Now we're going to look at particle motion. So suppose the graph below is showing the position of a particle. Where would the particle's velocity be 0? Where would its acceleration be 0? So if we're looking for velocity being 0, we know that velocity is the first derivative of position. So we're looking for f prime to be equal to 0. If we're looking for acceleration to be 0, we know that acceleration is the second derivative. So this is going to be f double prime is equal to 0. Okay, so the first things that we can do are our max min points, right? So here, 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 we're going to have velocity equals 0, velocity equals 0, velocity equals 0, velocity equals 0. And then our acceleration, we're looking for where this thing changes concavity. So we see concave down up until probably about here, and then it starts flipping, right? And pointing, instead of that way, it's pointing this way in towards, right? So here-ish, my acceleration is equal to 0. Same deal here, we go from concave up to concave down. So we'll go there-ish, acceleration is equal to 0. Here, this one, we've got a little bit more distance. We go from concave down to concave up, kind of right around here. So we'll make that acceleration equal to 0. Okay, so we could say that our velocity is equal to 0 at 2, 4, 5.5-ish, and 9-ish, right? You could say where our accelerations are equal to 0, okay? So there's kind of more of an application. And now we'll do some examples. So suppose a particle's motion is described by the equation. We've got s at t is equal to t cubed minus 3t plus 3. We're going to find the velocity, so remember that that just is the derivative, so we can call it v at t. We know that that's s prime at t, so it's going to be 3t squared minus 3. If we want to find the acceleration, we're doing s double prime, or we could do the derivative of this one, which is essentially what we're doing, right? But we could also write it as v prime. So the 2 is going to come down, we're going to have 6t, and then minus 3 obviously cancels, so our acceleration is 6 times whatever the time is, okay? If we describe the motion of the particle, we're going to kind of do that graphically. So the first thing that I'm going to do is I'm just going to get some starting points. So I'm going to say, okay, what's my position when 0 time has passed? If I plug a 0 into this original equation up here, I'm going to have 0 plus 0, so 3. If I want to find my position at 1 second, again, I'm plugging a 1 in, I'm going to get 1 this time. So if I kind of think about, okay, here's my start point. My position is 3. It goes back to a 1, right? So here's 3, here's 1. And then we need to think about, okay, what's going to happen there, right? I kind of gave it away. Does it start to turn around? Does it keep going the same direction? So we need to figure out where the velocity is equal to 0. Because right now we would say that that's traveling with a negative velocity, and then perhaps it continues, or maybe it loops around, right? So I'm going to set this thing equal to 0. So we're going to do equal 0. We're going to factor out a 3, so 3t squared minus 1. Divide both sides by 3, it just goes away, so factor this guy. So t plus 1, t minus 1 equals 0. So then obviously t is equal to negative 1, t is equal to positive 1. Time being equal to negative doesn't make any sense, so t is equal to positive 1 when my velocity is 0 and then changes direction. So then if I go back down to here, it's going to go something like that. Okay, and it's going to extend that way because it doesn't ever go back to 0. So I know my velocity is positive for the rest of this particle's motion. We can also use derivatives to describe stuff in words. So What's the second derivative described in each? Describe the concavity. So when he saw the yellow light, he floored it. Okay, so we know from driving cars that when we floor it, we're accelerating. Okay, so acceleration. Okay, because we're speeding up, that would be a positive acceleration, right? Slowing down is a negative acceleration. Okay, if we think about this as a distance function, we can say that our like a distance time or displacement time or position time or whatever you're looking at, distance function would be concave up, right? Because it would go, right? Because our velocity is increasing, we are accelerating. Okay. As the immunization program took hold, the rate of new infections decreased dramatically. Hopefully that happens soon, hey? So first I'm just going to talk about what these derivatives mean. So the first derivative would be the rate of new infections, right? If we're plotting time versus number of new infections, then the first derivative would be the rate of how many are happening, right? Then the second derivative would be how that rate of new infections is increasing. Okay, so if the rate of new infections decreased, then this is decreasing, so then this is going down. So the graph of new infections versus time would be concave down. So this whole thing is negative. Right, so the graph might look like that. Cool? You can't answer. That is so ingrained in me. If we're given information about f prime or f double prime, we can actually use that to sketch f, right? So just like we can take f prime and find out what the original function was, we can do that with an actual graph. Okay, so each of these represents a derivative. We want to figure out what the original graph looks like. So I'm going to do them one at a time, kind of like same 4-quadrant style. So here is graph 1. So how we tend to do this is we look at, okay, this is the slope, this is the derivative, okay? So if my derivative is equal to 0 at this point right here, then the slope on this graph has to be equal to 0. So what we do here is we kind of draw little ticks at that x value to say, okay, wherever this graph ends up falling, wherever, whatever y value it is, its slope is 0. Right, so we know that it's going to just pass through that point at a 0 slope, so it's going to be exactly horizontal. Here we've got the biggest positive slope, the biggest positive derivative, because we've got the biggest positive value on that graph. So we'll just call that here. So to draw the biggest positive value, I just draw nice positive, right? See how those are all positively sloped there? And then same deal over here. This is the highest, the most negative that this value gets, and it's about equal distance from the origin. So we're going to go, okay, this is a fairly steep negative little tick. Okay, as we get farther towards infinity, notice how this thing is staying positive, but it's a lower positive number, meaning that my slope is still positive, but kind of mellowed out. Over here, that slope is still negative, but kind of mellowed out, so it's less steep. So then I can kind of look at this pattern and I can say, okay, it's going from a negative slope to a steeper negative slope, flattening out to a positive slope to a less steep positive slope. So I'm just going to take a kind of series of these lines and turn them into a graph. And that could be my f prime. Now remember that that C value, depending on what it is, and we can't see that in this graph, would shift this thing up and down. So this would have been the same and totally acceptable compared to that, right? So both of those would work. They just have different C values, different vertical translations. So next one, here's graph 2. So this one, we see a slope of 0 happening twice, right? Remember that this is, the y value here is the derivative. So if my derivative is 0, that means that here and here, so let's go here and here, we've got that horizontal tangent. Here at the y-axis, we've got the biggest positive value. So I'm going to draw nice, steep, positive slopes. In between those, notice how here I've got a positive value, and again, I'm not looking at the slope of this graph, I'm looking at the actual, like, this could be a 3, this could be a 1.5 kind of deal, right? A 3 is a nice steep slope, a 1.5, it's still positive 1.5, but it's more of a mellow positive slope. Same with over here, so more mellow positive slope again. Then over here, we've got, it just keeps getting more and more and more negative. So I'm going to go mellow, steep, and then again, mellow, steep. So again, we can kind of use bits and pieces of this to connect a graph. So I'm going to go bloop, 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 like that. And there is what could give me the derivative to look like that. Third one. So I need to see that one. So this time we've got 1, 2, 3 points where this derivative is equal to 0. So we've got a tangent of 0 here. We've got a tangent of 0 here. And we've got a tangent of 0 here. Okay. In between these two, we've got the steepest, kind of right in the middle, we've got the steepest negative slope that it gets to. So I'm going to just draw these as nice, big, steep negative. Here we've got the steepest positive slope that it gets to in between those. And then here we've got negatives. Here we've got positives. So then again, we can draw a picture of this graph. So we've got kind of something like that. So we know that if we have a degree 4 function, then its derivative is degree 3. This one's a little bit tricky, so we've got straight lines. What does it mean to have a derivative that is a straight line? That should mean that our slope is constant, right? So it's not changing. So we've got a positive slope, a negative slope, a positive slope, and all of the slope values between these 2 points are the same. Okay? What does it mean that we've got discontinuities in our derivative? Our derivative doesn't exist. So that must mean it's a corner, or a cusp, or a tangent, some sort of thing that those derivatives can't exist. So I'm going to draw these as corners. So I'm going to have a corner and a corner. Okay? If I've got, this is a negative slope. So I'm going to go just kind of arbitrarily, boom. There's a negative slope that exists between those 2 points. Then to the right of this right corner, I've got a positive slope. Boom. To the left of this guy, I've got a positive slope. So there is a potential graph that the graph of its derivative could look like this, right? Because it's not differentiable here. That's why we've got the discontinuities there. and it's got a negative slope that's constant, and then positive slope that are both constant. The last thing that we can do here is, given the following information, we're going to find the absolute extrema, points of inflection, and a possible graph of f if it's continuous on the interval 0 to 3. Okay, so we've got a whole bunch of information here. We've got f prime, and f double prime for a bunch of different values of x. So we've got f, so if we wanted to sketch the actual graph, if we want to sketch f, we can say, okay, well, at x equals 0, the actual function is equal to 0. So I'm going to plot those points first. So we're going to go 1, 2, 3, and then 1, 2, -1, -2. So at x equals 0, the function is equal to 0. At x equals 1, f is equal to 2. At x equals 2, the function is equal to 0. At x equals 3, the function is equal to -2. So there's kind of my points, and we can kind of see, okay, maybe it looks something like that. We don't know yet. Okay, then we look at f prime. So f prime is equal to 3. So that means that this here is a positive slope over here, right? F prime is equal to 0. So that must mean that this tangent has to be equal to 0. This, if f prime does not exist, then here we must have some sort of cusp or corner or something non-differentiable, right? At that x value is 2. And then here we've got a derivative that's negative, so we know we're going to have a negative slope of that tangent. If we've got f double prime, so it's equal to 0 here, so that would be a point of inflection. It's equal to -1 here, so it should be concave down. It's not going to exist there. And then if it's 0 there, that's another point of inflection. Okay. Then we're going to say, okay, well, here's what's happening between these boundaries. So f between 0 and 1 is positive, so it should be on the positive side of the axis, so we know that, that's good. And then it's negative, which we kind of already guessed, right? Positive, positive, negative. It's going to be, the derivative is going to be positive, negative, so this is our max. If the derivative exists for all of those points, I'm going to draw it kind of like a parabola there, right? F double prime is negative, and you can see how that whole thing is concave down. Here, we've got it, it's going to be a negative graph. The first derivative is negative, so it can't go it could. It can't go like this though, because that doesn't make it not differentiable there. So it still needs to have a decreasing slope, but it needs to be some sort of cusp or corner. So I'm going to draw it like that. So see that difference between that line and one that could exist there? Because that would make it continuous and therefore differentiable there, right? Whereas this still has that negative slope to give that negative first derivative. It's still concave down, right? There's my little sad face. And so it fits all of these rules. So this would also be something that I could kind of give you guys and you could draw. So there's the second half of 5.3. You should be able to do all the practice questions about this as well as the ones in the assignment. The assignment for once is actually in order of all the things that you've done. So kind of when it gets to a point where you're like, I haven't done this before, that's a good place to stop. Again, let me know if there's any questions about this through email or the next time we see each other in Google Hangout. Okay, bye.